There we go. Okay. All right. Well, thank you once again for joining us. Today we have Dr. Sherilyn Willaims-Stroud with us. She is a structural geologist with the Illinois State Geological Survey and also president of Confractus Incorporated, where she does specialized structural geology consulting in the oil and gas sector. Her areas of expertise include structural and fracture analyses and modeling for geoenergy production, with a specialization in microseismic data interpretation and induced seismicity. She began her career at the USGS doing research in the Energy Resources Branch and also oversaw several USGS shared facilities, including the Core Research Center, the Nuclear Reactor Facility, and the Microbeam Lab. She has also spent time as a senior research scientist with Chevron Texaco exploration and production technology, while also teaching at the University of Houston. She was a full-time faculty member at Whittier College when she joined Midland Valley Exploration, a software and consulting company in Glasgow, Scotland. And as the geology team leader and the technical lead, she was the technical lead for their development of their fracture modeling module. After Midland Valley, she joined Microseismic Incorporated, where prior to becoming their chief geologist, she partnered with the chief geophysicist to develop and patent a methodology to integrate microseismic data into geologic interpretations for fracture modeling of microseismic results for use in reservoir simulations. And prior to establishing Confractus, she was a senior geological advisor with Occidental Oil and Gas and California Resources Incorporated, working on fractured reservoir interpretation from various Oxy assets, including the Monterey Formation. In addition to teaching industry short courses, she has also held an adjunct position at the California State University, Los Angeles, and Northridge. And she is an active member of several professional organizations and is also an AAPG visiting geoscientist, where she visits colleges and universities to present both technical and career-related talks. She served for 4 years as a member of the National Academies of Sciences, Engineering, and Medicine Committee on Seismology and Geodynamics, and continues the pursuit of integrating scientific knowledge related to induced and natural earthquakes and translating that knowledge to the general public. Dr. Willaims-Stroud received her Bachelor of Arts in Geology from Oberlin College, followed by both a master's and a PhD from the Johns Hopkins University, and she is also a licensed professional geologist in the state of California. So she is very impressive, and I'm honored to host her here today. And with that, I will let you take over. I will let you present, and then we will have a Q&A session. So if you have questions, there's a little Q&A box that you'll see. Go ahead and type your questions in there. Sometimes they get lost when you type them into the chat. But with that, I will let you take over.
Thank you. And thank you for inviting me and to David Haddad, because he asked me if I wanted to give a talk here. And I'm going to give just a sort of an overview of what we're doing at the Illinois State Geological Survey on our CO2 sequestration projects. And you may have heard about the Decatur Project, and that's one that we have the most data from, but I'll include data from, there's a second project at the same site, and I'll include data from that and show you what we learned about the subsurface and how this reservoir reacts to injection of CO2. So first, I just wanted to familiarize you with some of the initiatives that are underway to accelerate CCUS. There were originally 7 of these, and now they've been narrowed down to 5. And we're actually in the Midwest Regional Carbon Initiative right here. And so these are the 3 states that the Illinois Basin covers. The little green line there, if you can see that, is the outline of the Illinois Basin. And also the point for the targets for what we're doing in the Illinois Basin is to sort of, in the end, develop a whole entire Illinois storage corridor for storing, for sequestering CO2. And we have a bunch of industry partners. These projects are funded by DOE, but this is sort of a little timeline of expansion here. So IBDP was the first project which has completed, and we're in the middle of trying to put all the data together and package it in a way that's useful for everybody else to download, and we're delivering that to DOE this summer. The ICCS project is still underway. It's a little bit bigger than the IBDP project in the same location. Both of these are at Decatur. We have several other projects under this carbon safe program that are right now in the phase of sort of reservoir characterization. No injection has started in those yet. We're still trying to see what we can do there. But the goal is to get more than 50, to figure out where there's more than 50 million tons per year feasibility for injection. And then after we do that, then it'll go into the permitting phase. So the two projects I'm going to talk about today are both at Decatur, as I mentioned. The first one was the Illinois Basin Decatur project. The second one was the Illinois Industrial CCS project. So the Decatur project was, the goal for the Decatur project was to inject 1 million tons of CO2 in the subsurface over 3 years, and that was accomplished. And right there, we can see that they did it at about 1,100 tons per day. And we learned a lot about how the public might respond. And we worked a lot with Archer Daniels Midland to decide what to monitor and do the risk assessment. And just a little aside there, before I came here, I didn't even think about the fact that ethanol was not green, it's just renewable. So the fermenting process actually generates a lot of CO2. So the post-injection monitoring ended in April 2020. And as I said, we are in the process of packaging up that data for public distribution and the models. So all that will be out there. The Illinois Industrial CCS project is an industrial scale demonstration project. And the main difference between the IBDP project and ICCS project is that now ADM is injecting all of the CO2 that they generate. So now it's industrial scale. The intent was to inject up to 5 million tons over 3 years or longer. The injection capacity was 2,200 tons per day. The compression capacity was 2,200 tons per day. They're not injecting quite that much because that's, they're injecting what they have. It turned out to be around 1.5 times to 1.7 times the injection rate of the first project, the IBDP project. And that's still going on. And sorry, I didn't update. As to date, there have been more than 3 million tons injected for both of these sites together. All right, here's a detailed, a closer view of the Illinois Basin setting here, and the contours on this map are on the top of the Precambrian. And again, this is the outline of the Illinois Basin. And this little square here, where I put the red star on top, is the location of the two Decatur projects. And the stratigraphic column here shows the what our target is. Down here at the bottom is Mount Simon Sandstone. It's more or less on top of the basement. I'll give you some more details about the strat column later. But there's a shale, a major shale seal right on top of that. And then there are a couple of other sandstones that are potential reservoirs for CO2 injection. And these three, well, the Mount Simon is a brine. It contains a brine. It's not prospective for oil and gas. The St. Peter sandstone does produce oil and gas in some places. And both of these are also sinks sinks is the term if we're going to talk about it in terms of petroleum geology, oil and gas, but now we're injecting CO2. And then another seal And then the third seal, the New Albany Shale, which is also under consideration for unconventional resource production. So the main point I wanted to make with this slide is that the Mount Simon sandstone has 3 seals on top of it. Okay, this is what the site looks like, and we're looking at an air photo of Decatur. This is a mile, 1/2 mile right here, this arrow. And this is the sort of monitoring shallow surface monitoring setup we had for the Decatur area. And so this is a list of what all different kinds of wells we have here. But this is mostly looking for leaks to the surface. But after monitoring for ejection for the IBDP project, we realized that we didn't have to have that dense a network. And so this is what the network looked like at the surface for the second project, the ICCS project. And the result of that is that we collected data from over 1,400 shallow wells, so shallow meaning less than 100 meters. And these are the surface sort of collections, not the reservoir wells, 188 deep wells, including some that are only 1,000 feet. I'm putting meters here, but 1,000 feet, so 300 meters deep for groundwater, and 755 soil gas samples. And from all of those, there were no anomalous geochemical signals that indicated that there was leakage of CO2 from the Mount Simon. So I'm going to go into a description of the deep monitoring wells, right? So what we have here is, again, an air photo, and a lot of this is sort of the ADM facility down here in the southern part of this picture. And the CCS well is a class 6 permit well. And I think from what I understand, I only joined this project about 2.5 years ago, but class 6, I think, may not have actually existed before they started looking at this project and understanding what the considerations needed to be. But it's a class 6 well, injection well. And this is the red dot is the location of the CCS1 well, the injection well. And right next to it, there's a yellow dot called GM1. So that's for geophysical monitoring well. And that's the well that had the geophones in it for induced seismicity and vertical seismic profile acquisition and processing. And then up here, about maybe 1,000 meters away, is the VW1 well, or I think it's a mile away. VW1 well, which is no, that's not right. 500 meters away or so. VW1 well is the verification well. And this is the well that had constant temperature, pressure, and pressure monitoring. And we did repeat acquisition of geochemical indicators to see when the CO2 reached that well. So this is the setup in this darker green box for IBDP, the Illinois Basin Decatur Project. And then the lighter box is a similar setup. The lighter green box is a similar setup for the ICCS project. Again, there is a injection well, a geophysical monitoring well, and the verification well, monitoring pressure and other things. All right. Now I'm going to show you a cross section between these 4 wells. These are the 4 deep wells. All of these wells were drilled through the Mount Simon and into the very top of the Precambrian basement. And this is a cross section showing the well logs. And so basically, I'm not going to talk about the reservoir response in this slide, but what I want to show you here is the configuration setup. So here is the CCS1 well, the first well. And the perf zone is right here, represented by these black markers. The top of that perf zone is about minus 2,100 meters. And it's these perforations are right on top of this unit that used to be called the pre-Mount Simon, but now we're informally calling it the Argenta formation because we know it has a different source and it's a different unit than the Mount Simon reservoir. And obviously it's a different unit, you can tell by the logs, but there's a little bit of a disconformity in between these two. And this Argenta formation right here sits right on top of the Precambrian basement, which is granorrhyolite, right? So this red line here is Precambrian basement. The Argenta is gets thinner in some of the wells and thicker in other wells, and that's the on top of the basement, much lower porosity than the Mount Simon Sandstone reservoir, which was the target, and that is, we think, turned out to be very impactful with respect to what happened with the induced seismicity. The one of the important points here is that we did get induced seismicity. 90% of it occurred in the basement. So although we're injecting into the Mount Simon here and about 50 meters shallower is the bottom of this perf zone, most of the induced seismicity happened in the basement, which I'm sure a lot of you are familiar with when talking about wastewater injection. Now, we had an extensive imaging and monitoring, seismic monitoring program. And this is just a list of what we had out there. There were two 2D seismic profiles that had been acquired before the project that we integrated into the modeling, and then 4 high resolution 2D profiles that were taken just at the beginning of the profile that go through the site. I'll show you a map of those in a minute. And then the vertical seismic profile, again, was in the GM1 well that was right next to the first injection well. And the interesting thing about that is that that array in that well was put there for, originally the primary use of that was for VSP, and it ended up being very useful for monitoring the induced seismicity. There were 2 seismic surveys done. Basically, it looks like 4, but there was 2. First, there was a 3D seismic survey in January 2010, and then we realized that we needed to go further north, so they added another piece further to the north and integrated those into one survey to have enough coverage for both wells where they think there might be, we needed reservoir characterization. And then in 2015, was the time-lapse survey covering the same area of the combined 2010 and 2011 surveys. And we had the 2015 3D survey reprocessed because after seeing the induced seismicity, we knew that there had to be some faults in the area, but we couldn't see them in the first survey, so we had them reprocessed with newer methods in order to try to sort of tease out fault structures. All right, this is a map showing the survey acquisitions, all of the seismic acquisitions. I don't know if you can see this light blue line going through here. There's one like this and one going there. Those are the new 2D seismic lines that go through the site. And here is the footprint of the 3D seismic survey. And there was also seismometers installed on the surface. The yellow boxes are the USGS seismometers. That's their array for monitoring induced seismicity at Decatur. And the ISGS, the Illinois State Geological Survey seismometers, are the red ones. And one thing that's a little bit frustrating for me about this is that these didn't get installed until 18 months into the project. So because we have this wide azimuth coverage from the surface, we can get source mechanisms for some of the largest events, but not for some of the events that came in the beginning of the injection. And that's where a lot of the really interesting induced seismicity happens. Another thing that you can see here is that a lot of the induced seismicity is outside of the survey area, right? So although we have a nice model, and I'll show you that in the next few slides, a nice model of the subsurface in this in this area, we don't have any idea what it looks like, or a good idea of what it looks like over here outside of there where we have more induced seismicity. All right, this is my model using, I used the MOVE software from petroleum experts to put this together, but we did a lot of the modeling in Petrel as well, reservoir simulation modeling and some geomechanical modeling. And this is just to kind of show you relatively where we have data and where the model extent is. And I'm not showing all the horizons, but this is the Eau Claire Shale is this top blue layer here. This is the lighter brown layer is the top of the Mount Simon sandstone. Actually, I think that's Mount Simon D, and then there's another, the top is a little bit shallower than that. And then there's, all of these are Mount Simon. And then right below here, there's a sort of reddish one, which is the Argenta, which is really close to the Precambrian basement, and you can see the located induced seismic events. And now I turned all those off so you can see the topography of the basement and how it relates to the induced seismicity. And I'll talk about that a little bit more in detail later. This is the comparison of the first seismic processing and the second seismic processing. And I like to show things with no vertical exaggeration. So you can see here that there's not a whole lot going on in terms of structure and being able to identify faults. And this was originally, we just kind of, this was interpreted just as a slightly undulating surface here. But when we got the reprocessing done, we were able to kind of pick out things where you see these disturbances that might actually be faults. The red marker here is the top of the basement. And again, I want to point out that the big issue with this is that when you start going into the basement, there's not a big enough impedance contrast to really pick up layers. And so it was really tough to find faults in the basement. And so we think that, these areas where you see this disturbance might be faults. But the final interpretation actually didn't show a good correlation of the faulting, which was mostly interpreted in the shallower units above the basement in the Cambrian, and the induced seismicity, which was below. So they weren't actually co-located. There were some places where they intersected, but the relationship was not strong. All right, so also that when we got it reprocessed, Sterling Seismic did it. We had them do a porosity inversion, which was we got really excited when we saw this, because when you look at this, I've projected, I guess, induced events from about 100 meters away onto this cross section. You can see that the blue, this here is the Precambrian basement. So that's low porosity. And the blue up here is the Eau Claire Shale, low porosity again. And all the orange hot colors are the reservoir, the Mount Simon. And the thing that was really nice about this reprocessing is that the Argenta made a really distinct difference between the blue in the basement and the orange in the Precambrian. The orange in the Cambrian Mount Simon. And this is the part that was really interesting, that when you look at how thick the Argenta is here and in this well, it looks like in this cross section, there are places where that Argenta is either missing or very, very thin, where my arrow is pointing. So if you blow that up, you can see other things that we interpreted based on all the other well data and the seismic, is that we think there's a fault right here. That fault could go up all the way through that, but it may just be an early fault and the Argenta filled in there. And there's these little green streaks in the permeability log here that represent low permeability baffles, is what we call them, because they're discontinuous. So these are all through the reservoir and they restrict vertical flow. And so one of the things that we started to think about was when you inject into the Mount Simon A, which if you remember from the well log cross section, the injection zone was right here at the bottom of the Mount Simon A, just above the Argenta. You could get these sandstone units have pretty high porosity and permeability. It could be up to, averages like 250 millidarcies, and it could be up to 1,000 in some places. And in this case, it looks like you could inject and have mostly horizontal flow, or have horizontal preferential horizontal flow and meet some of these baffles. The dots here mean that this may not be the same baffle. It's just saying that there's a baffle here and a baffle there. It can meet some of these baffles, and then the pressure could build up below the baffles, or build up below, because it's not it's close to the basement, but actually migrate over to where this fault is and where this area of potentially missing Argenta is, and get into the basement that way. So you could consider the Argenta a bottom seal, and that maybe it's not here right now at this location, and that might be the reason why we got induced seismicity. All right, now I want to talk a little bit about induced seismicity, so you have a reference for how big these events are. And I got this table from the British Geological Survey, and just to remind you, a -3 magnitude earthquake is really small. It's like 1 kilogram dropped 20 centimeters. So there's 1 kilogram of apples. You just dropped them from off the table or something. Well, less than the table. It's lower. And then a powerful slingshot, we -2. A 100 kilogram person jumps down 2 meters. There's Michael Jordan's earthquake. And then there's a magnitude 0 is 15 grams of TNT. And this is generally, I think, considered the range of microseismicity. If you get above that, it's starting to be regular seismicity. Regional networks can pick up magnitude 2 earthquakes. Maybe can't locate them very well, but they can detect them. Magnitude 3 are earthquakes that people might start to be able to feel. And I like to add this one because 100 joules is somewhere in here. And I put that there because I used to play softball. So I like that there's energy there too. Okay, so now I want to talk about the injection periods for the two projects. So injection started in the IBDP, the first project, in 2011, right? And then there was a lull, mostly because it took longer to get the permits in place. But originally, the project wanted to be able to have injection of both wells happening in both wells at the same time to see how the plumes might interact. But instead, we had a almost 2-year hiatus, and then started injecting again in April of 2017. And as I said before, this injection is still happening. And here's a map of the induced events. And I just want to show you the injection rates relative to the event frequency. And here you can see that it comes in bursts, despite the fact that the injection rate is more or less constant. Sorry, this is the downhole pressure. The blue is the injection rate, and the orange is the injection pressure, right? So there are a couple of places where there were small period shutdowns for mechanical reasons, and then, but most of these events, these bursts, don't really, I know you're familiar with looking at hydraulic fracturing pressure rate curves and event rate curves that have a much better correlation than this. These are kind of almost constant, and then we have these bursts here of different, and all of these bursts are basically temporal. So if you look at this first one, this cluster right here happened during the first few months. Well, actually the first few months, not much happened at all. And then all of a sudden, about 3 or 4 months later, a lot of activity started happening here. And then in the summer of 2012, right before the surface seismometers were installed, this cluster happened. All right, so that most of these bursts correlate to one of these clusters. But if you go on to look at the induced seismicity that happened, or the seismicity during the period where there was no injection, you see it's happening pretty much all over, right? So that's definitely not correlated to injection rates. And then after the injection into the second well, not too much was happening, right? It's it looks like the same rate to me. And then the thing that's interesting is that it's 1.7 times average the rate of injection of the first well, and you don't get a lot of induced seismicity. And as I say, we're still injecting in that well, and you get something on the order of a few events per month, and they're smaller. All right, so let's go back to this reservoir response log. So what the point for this that I wanted to make for this was we've got injection down here on the top of the, at the top of the Argenta, base of the Mount Simon. There's mudstone baffles that go between these wells. Because you're close to the basement and apparently close to this location where there may be little bottom seal or no bottom seal, there is probably a number of good pathways for fluid pressure into the basement. It would be nice if we had pressure monitoring the basement, but we don't. So we just have to infer what the pressures might be down there. But then compare that to the injection zone of the CCS2 well, the second well, where the difference between the top of the lower injection zone is the injection zone is CCS1, and the injection and the bottom of the injection zone is CCS2 is less than 50 meters. And this is a much thicker injection zone. And what happens in this case is maybe all of these baffles are inhibiting flow to the point where all the pressure just stays up here. And I'm going to show you some pressure information later, but but go back and, if you remember the slide I just showed you, very few events are happening during injection in this zone, even though the injection rate is much higher. All right, so the pressure this is where the pressure was increasing. So each one of these are pressure gauges in the verification well. And what I'm showing is the highest pressure increase from above background pressure, right? So the highest pressure increase was in the measured in the VW1 well, which was 1.17 megapascals over the hydrostatic pore pressure, which was about 23 megapascals. And then, but nothing happened up here, right? So all of these were lower. And then also interesting to see that it's also lower in this, the increase was lower, if that makes sense, in this lower pressure gauge depth. And then after injection in the second well, we got much higher increases in pressure. I shouldn't say much higher, higher increases in pressure, 2.3 megapascals for this gauge right here. And also it made it all the way over to the pressure gauges in the VW1 well with a higher pressure increase as well, 1.64. So that's reflective of the high permeability and porosity of this zone, but it's not going down in this case. It even migrated up higher to, this is not actually a gauge, this is sort of the a place where we can measure pressure at the bottom of casing there. So all of this means that, there must be discontinuous baffles, right? So horizontal flow is preferred, but eventually it gets up to different locations. I didn't put the times of these locations here. I know our one of our geoscientists here is working out the great detail, the timing of when these things happen. But all I'm showing here is sort of a synopsis showing what the maximum pressure increase was. And because of that, we decided we would model the reservoir with these sort of stochastically generated baffles of lower permeability. And it worked pretty well because I think we got a pretty good match with our simulation models, and we're working on publishing that, putting that out as soon as we can. All right, here's another view of the microseismic events, induced events in the reservoir on the top of the Precambrian. And one thing that you can see here is where we've interpreted the faults. And these are very small offset faults in this, on the order of, dozens of, no more than 10 to 30 meters offset, but most of them are much smaller than that. So it's very interpretive, I have to say. I'm not showing the faults, but you can see these little gaps here where there are faults in the Precambrian. Actually, this is on top of the, no, this is top of the Precambrian. But one thing that's interesting is like this high here where the Argenta may be missing, also seems to be the location of a lot of induced seismicity. So this part might be very highly fractured. And this is just a depth view of the same thing. I talked about the induced seismicity spikes before, and now I'm showing you where they are specifically. This spike correlates to this cluster in depth and in map oblique view. All right, so a few words about about historical seismicity, because that's always the sort of concern of people when you're injecting, and whether you're gonna. We know that the New Madrid seismic zone, which, sorry, I should have moved that, is here. This NMSZ should be here. Has natural seismicity, significant natural seismicity. There have been large earthquakes there. And the beach balls that I have on here are earthquakes. Most of them are, they're all above magnitude 4. Actually not. One of them was a 3.8, but it looks like the stress state from these natural earthquakes is strike slip. This is what we've also measured in the well bores from sonic logs and rock mechanics property processing. And the point I wanted to make with this slide is here we are right here in this area where there's not as much induced seismicity. Sorry, the blue dots are wells. The brown and purple dots are seismic or natural earthquakes. But if you take an area like this around the well, the site, you can see this is probably the largest earthquake in that area. It's about 100. This circle is about 100 kilometers radius. This one is the largest historical earthquake within 100 kilometers of this area was magnitude 2.7. Right. So that's not this one. This one's outside of. Sorry, this should be centered on the event. So it would be one of these down here. Anyway, I thought that, and so our idea was that because historically there's not a lot of large earthquakes here, or not a lot of seismicity at all here, that supports the idea that there aren't a lot of large faults in the reservoir area that we're injecting into, and also that is supported by what we see in the reflection seismic data, because it was so hard to identify them. All right, those are the earthquakes within 100 kilometers. All right, so I wanted to compare this to wastewater injection, and the rates are similar, right? But we still don't get a lot of, we still don't get felt seismicity. We got significant induced seismicity, but it was in the microseismicity range. The largest induced event we've actually recalibrated. It was 1.5, magnitude 1.5, but none of this was felt for either well, right? But then when you compare that to wastewater injection, we have similar kind of injection rates here, 1,950, about 2,000 event meters cubed per day or more. And you start to get felt and significant. This could be, depending where you are, that could be a damaging earthquake. But I also want to draw your attention to the Williston Basin here, where the injection rate is much higher, and they also get some induced seismicity, maybe a little bit bigger here because they're much larger injection rates, but maybe there's some that you might be able to apply the same rationale to the Williston Basin as the Illinois Basin, in that you've got to have big faults to have big earthquakes. All right, and other issues to think about for injection of CO2 is that it's not the same as water. Even if you inject the same amounts per day, we have seen lots of large and felt and even damaging events from wastewater injection. So far, none in CO2. And this is not just from IBDP. Other CO2 injection projects also have induced seismicity, but not felt seismicity. I think that some of the issues that need to be addressed are the fact that supercritical CO2 behaves more like a gas than like water, which is incompressible, and there may be dissolution effects, and water is denser than CO2, and then other water rock interaction issues. So I think there's a lot more to be learned about this as we go on. So basically by reprocessing the seismic and comparing it to the induced seismicity, we've found that there are faults in the basement that we can see, that we can infer from the induced seismicity. And in one case, there was a hydraulic connection to the basement, and in another case, there was not. So you can't assume that you're going to get induced seismicity. And once you learn what the salient characteristics of your reservoir are, you can probably avoid it. But the other thing we learned that there were large uncertainties for pre-injection fault identification in this case. As I keep saying, there are small vertical offset faults. We weren't able to confidently identify them. We were comfortable with our interpretation in the end, but there's still a lot of uncertainty to it. The downside of that is that it's not useful for identifying reactivation risk prior to injection. But the upside is that maybe it means that you have lower reactivation risk. And the other point was that the seismicity in this case was not closely tied to injection rates. And I want to acknowledge that the people, the projects that we've collaborated with and funders with on this CO2, the Decatur projects. So, and I already mentioned the Midwest Geological Sequestration Consortium. That was in the first map I showed you. And the Carbon Safe Illinois projects all of these are funded by DOE, and we extensively use Petroleum Experts software and Schlumberger software, which they generously donated to the project. So thank you very much. I think I left time for questions. I don't usually.
Yeah, that was wonderful. Thank you very much. That was really good. Are you able to see the questions or the chat on your side? So we did have a couple questions come in on the Q&A part, and I believe there is one in the chat. And we can, if you're not able to see that, I can read those to you.
I can see them. Hold on. Okay, now that I turn that on, okay, I need to try to go to the screen. Okay, I just wanted to stop sharing.
Okay.
Because I have some extra slides in case people see that might address some of the questions. Okay, so I see Gary Roll. Did you see a pressure transfer from injection zones to seismogenic zones? No, because we have no pressure gauges in the seismogenic zones. That's the main reason. So can't answer that. Colin Sayers, was the seismic reprocessing pre-stack time or pre-stack depth? I don't know. Wait, pre-stack, I'd have to look. I don't know. I would like to know why that, what that would tell you. But I can't answer that question without going back and looking at the files because I don't pay attention to that kind of stuff. Sorry. Zach Williams. Okay, Molly? Oh, what does that say? Is it, do you? Okay, Zach Williams. Were seismic attributes like coherence used to try and find suspected faults? We've tried to use that, and I will show you. So one of our Schlumberger collaborators used the Schlumberger, the Petrel ant tracking to try to identify faults, and I'm going to show you what he came up with. One of the problems with this data set is that it's a really, it was a really weird acquisition. The receivers were like 10 feet apart and the sources were 80 feet apart. So it was very anisotropic. And we did ask Sterling Seismic to do that, and they said they couldn't do it. It didn't work. Well, I mean, it just, like when you look at the images, it just doesn't show anything. But in the end, Wade Zaleski at Schlumberger, this is an example of what he came up with doing the ant tracking algorithm. So, like for instance, right here, I don't know if you can see this very well. Where's my mouse? Oops. Okay. Okay. So here's my mouse. We've interpreted a fault here, right? And the ant tracking actually identified faults there and here as well. And there, I don't agree with necessarily making these faults, extending this fault from here all the way down to there. I think that, and then when you look at the fault surfaces, you can actually see that there's patches of displacement. So I think those small patches of, 10 to 20 meters of displacement represent different faults or different splays, related to that fault. But there's nothing here. There's nothing interpreted there. There are places where there's not really offset where you get these things. So I wouldn't put a lot of stake in the ant tracking fault identification. And then just to test it, Wade created surfaces for all of these ant tracking identified features, and I made them into faults and turned them and did a orientation analysis of it, and it's all over the place. And it's sort of just the same intensity in the Mount Simon as it is in the basement, which we don't see in the well logs. So I don't have a lot of confidence in it. Chris Walker said, oh, thank you, Chris. Was USGS network installed pre-injection, and did it determine any background seismicity in the area pre-injection? The answer is no. And it wouldn't, we did have the wellbore geophones installed pre-injection, and they monitored for 18 months prior to injection and detected what was determined to be natural seismicity was only 8 events, and they were all very small, so the USGS network wouldn't have been able to detect them anyway. Clinton Tippett, can you comment on the age and composition of the Argenta formation? Yeah, I didn't say that. Okay. The Precambrian basement, right? The Argenta is 540 million years old, right? What we've identified, well, I didn't, but our stratigraphers identified some trace fossils in there. So we know it's not Cambrian. There may be a 900 million year hiatus between the last, the Precambrian rocks, the volcanic rocks, and the Argenta, and it's sort of an arcosic sandstone. Michael Gross, thank you, Michael. Does the alignment of microseismicity identify other potential faults or fracture zones? Yes. That's what we think. Okay. So Gretchen wants to know, hi, Gretchen, if you have lots of geoscientists are making career transitions or new graduates are wondering about opportunities to work in CCS, can you please advise about the opportunities you see in the past to get into this type of work? I think it's an area ripe for expansion. As I said, what we're working on is expanding just the Illinois storage corridor, right? This is not the only place that's suitable for CCUS. We have lots of industry partners. Our industry partners in the southern part of Illinois is a coal-fired electric plant, and they're doing beautiful, clean coal. I mean, they have scrubbers already installed. They're working with us to figure out a way to get rid of all their CO2. And the backgrounds of petroleum geoscientists is perfect for this. I just think it's a perfect transition industry for petroleum. And I know the companies are doing that. Okay. Doug Carlson, how is the CO2 gathered before injection? Does the CO2 go down the well bore 99% CO2? I don't know how it's gathered. That's an ADM and an engineering question. And I think the answer to your second question is yes, but I would have to defer to an engineer who knows more about that to me. So don't take my answer as a given. Clinton Tibbet, is the CO2 injected as liquid or as a gas? It's supercritical CO2. So yes, and yes. Supercritical. I don't know. That's not either one, actually, is it? Jim Tucker, it sounded like the project injected carbon dioxide gas rather than supercritical CO2. No, it injected supercritical CO2. It was supercritical CO2. I do know that. Was it possible to determine it? Okay, supercritical CO2, it was a few degrees, like 4 degrees centigrade, um, colder than the reservoir, not that much colder than the reservoir. I remember one of our engineering geologists saying that recently. And at that depth and pressure, it's supercritical. Was it possible to determine or see the injected CO2 volume in after injection CO2 seismic survey? The Schlumberger modelers say yes. I'm not convinced. We have a little plume of pressure that's concentrated just around the wellbore that was created from the time lapse, but I'm not sure. I'm not convinced. We do have a modeled plume though. I'm not an RE, but the rock physics at this John Hooper have said in the past the CO2, while the gas behaves more like oil when injected and is miscible with oil. Yes, different problems. But what's the phase behavior and compressibility versus injected wastewater? That's I can't answer that question. I'm not a reservoir engineer or geochemist, but I think that's a great question, and that's an area that needs better understanding and more research. Gary Rull, do you have any water samples taken from the basement? That's a good question. I will find out. I don't know. I don't think so. I think they just drilled. I don't know. That's a good question. Steve Hadaway, can you tell us the volume of a ton of CO2, possibly in thousands of cubic feet? I think it's close to this because I showed that slide that had this slide, cubic meters per day, and I also showed that the injection rate was about 1,000 tons per day. So they're similar. But I'm not the best person to answer that either. Luke Fresh, time sequence of seismicity. I saw your differentiation between events during injection versus not, but significant induced seismicity can occur even after injection stops. Did you look at this data with more granularity than what you showed, and did it show anything interesting? Okay. If you mean this data here, can you see my, so this is where injection stopped, right? There was a little bit of seismicity still happening. Some people might call that a surge in seismicity. I say it's a small increase in seismicity, and then it went down. But to answer your other question, we did look at induced seismicity in general with more granularity. And you can see, for instance, this cluster indicates fault splays within that event, within that cluster. So that's why going back to Michael Gross's question, that's why I think that it might be fracture zones that are being lit up and not faults. You see things that look like these little temporal bursts that have a different orientation than the whole cluster has. Faisal Anwar, is it possible to generate additional minor faults during the injection process? No, I would say no, because the injection was always below the frac gradient. So we're not ever generating more faults. We're just reactivating what's there. Steve Hadaway, thank you. Thank you, Steve. Also, I saw that the injected CO2 was liquid, so I learned a lot today. Thanks, Steve. I'm glad I was useful. Michelle Pettinger, is there any correlation between the induced seismicity events and the CO2 plume location if you have data to indicate plume locations? We do have data to indicate plume locations. And, you know, I said I was skeptical of the plume that was modeled from the seismic reflection data, but we do have information about where the plume was from the monitoring wells, right? So we know how far the CO2 went. And the answer to that question is the correlation is not strong at all, right? I've seen, so the plume within the Mount Simon moves out kind of in a regular fashion, but the events kind of, you know, it moves out and then it pops in one location, and then later on it pops in a different location that's closer to the well. So we saw a lot of that, especially when you look at it in relatively short time periods. Felicitas Kaiser, thank you. Does the preferred horizontal flow occur in direction of SH max? No, I don't think that there is, that's what's happening in the Mount Simon. But we don't know. And because if you remember, the wells are basically in a north-south line, right? So what we're monitoring is when it gets to north of the injection site or northwest of the injection site. And if you're monitoring that, it's flowing in, we don't know if it's flowing to the direction that the wells aren't in the line of. So I can't answer that from the wells, from the well data. John Hooper, also wastewater has some possibility of softening rock response and reducing rock strength. What does CO2 do to rock strength? I think, yes, that's a good question. I think that can happen depending on what the rock is, right? And I think that there are some people that work on that. I don't know a lot about that, but I know that that isn't a possibility. Clinton Tippett, if you had known that the pilot sites were right about the window in the Argenta, would you have located it somewhere else? Yes. We have some other places where we're looking at well locations where we think that might be happening, and we don't want to put the well there. Is the window a fatal flaw for injection into the lower Mount Simon in the pilot area? No, I would say no, because although we got induced seismicity, it wasn't felt seismicity, right? And that's true in this. I say no in this case because of the fact that we're in a low seismicity area, natural seismicity area. The induced seismicity was small. There's always a chance that it could be bigger than what we saw if we increase the injection rate in the Mount Simon in the first well. But I am not expecting that it will be large, felt seismicity. I could be wrong, but I'm not expecting that it would be felt seismicity because of what we think we know about the reservoir and the kinds of faults that are there. Did I get everywhere? Did I get this question, Michelle Pettinger? Is there any correlation between? Okay, yeah, I got that one. All right, I think I got all the questions. If there's somebody, if I missed anybody.
There may be one or two that got thrown in the chat.
Okay. Oh, I see 4. Okay, were you able to get a sense of the strike of the faults mapped in seismic? Oh, so I apologize. I didn't show a picture of the faults. I don't know if I have one here. I should have done that. Hold on. Let me see if I have one. A fault map. I have a couple of slides that might help. Okay. So this is from one of our, this is before we smoothed out the faults, right? So you can see the sort of jaggedy lines there that the faults on top of the induced seismicity, right? So mostly this is our first basement interpretation. So that's why it's square, because we had to interpolate here because there's no seismic data right here. But in the second version, we just left that out. And then, so these events are mostly this orientation. The clusters are mostly northeast southwest, which is consistent with strike slip failure on strike slip oriented clusters. So some of these faults actually cut across, in this case, this cluster. And when you look at this cluster, you can see these, it's small details, time periods, like 6 hours. You can see this is where this is a 6 hour cluster burst right there, right? Sorry. And this one I like because it's showing, this is a couple of faults that cross this big cluster here. And these events are colored by time, and I compressed it because most of them are coming in the beginning, right? So I had to compress the time scale in the beginning because I'm showing all the events, and the red events are the ones that are mostly happening during non-injection and the second injection, right? So if you have blue and red, that means you have something that happened very near the beginning and something that happened also near the end again. And these are a couple of faults that are interesting. And this is showing the same thing rotated down 33 1/3 degrees. So you can see where this fault, these faults actually cross this cluster. And this fault might actually be a fault that's where the clusters or fracture orientations, fracture reactivations get stopped because there's something right here that's not oriented to slip. Right, so yeah, and the other thing I wanted to show you with this in terms of details, I tried to map out where things are going. So it goes like the sequence is 1, 2, 3, 4, 5, 6. So it's not like it's going in sequence away from the well. I think when I did that, okay, one open question. I don't know if I got all the questions. Are there any pieces of evidence that indicate subsidence around the study area? Yes, but I'm not, yeah, I would have to say yes, but I'm not the one to ask about that. So, but that's a good question. I think there is normal faulting, but I think the other thing is that there is significant strike slip faulting in the stress regime right now. It's still strike slip. That was one of the things that could be concerning if you're worried about large earthquakes, because even though just because you can't see the vertical displacement doesn't mean that there's significant strike slip displacement, and that is the thing that could lead to large seismic events. But as I said before, looking at the fine detail in these clusters, it looks like what happened in the basement, what's being reactivated in the basement is fracture zones and not large faults. Thank you, Luke. Okay, I don't know if I got everything. Who is that? Trevor Atkinson. The answer to your question is yes, there has been a lot of talk about thermal energy storage in the Decatur Basin. Did we see salt precipitation in wells reducing injectivity? We saw something that reduced injectivity in some of the wells, but I don't know. Sorry, I don't know a whole lot about that, but I don't think it was a big issue. Okay, Molly. Oh, so that's Gretchen saying Molly. I guess she had to leave. Gretchen is thanking us. You're welcome, Gretchen. Nice to see you. And I see I answered Elena's question talking about the strike slip. Hi, Fuller.
Hi, Fola.
Oh, what was the CO2 source for these projects? That was anthropogenic CO2. It's CO2 generated from fermentation of ethanol, which is from corn, which we have a lot of here, which is not green, it's just renewable. It's green if you inject the CO2. Okay, we went 5 minutes over.
Yeah, you did great. You did awesome answering those questions. That was perfect.
Well, they were great questions. I have fun answering questions like that.
Yeah, awesome. Well, thank you so much. It was an honor having you here, and thank you to all the attendees. I really do appreciate it. And I guess that's it. If I didn't have anything else to say except thank you. And you're getting a lot coming through on the chat. Great talk. Many thanks.
I
Very
have.
good. Awesome. Well, thank
Yes.
you so much. And I will keep in touch. This has been wonderful. You've done some very awesome work, and it's been an honor hosting you today.
Well, thank you for inviting me. It was my pleasure. I enjoyed it.
Thank you so much.
Bye-bye.
All right. Bye.